Hi, this is the video record of for those who miss the lessons on waves after the first lesson of waves, where we learn our wavelength and amplitude. So carry on from wavelength and amplitude. If you remember, the very first lesson you have already learned about um, how to tell the amplitude from here. Okay, amplitude, the maximum displacement. Okay, maximum displacement from rest position to the top or to the bottom. That's the amplitude, right? Amplitude. That was a recap. And then we also learned about wavelength, which is a measurement of two points that is moving, two consecutive points that is moving in the same direction, same speed. Okay, so that's the wavelength. It can be from crest to crest or trough to trough or one complete letter S, right? One complete letter S, uh, one complete wave. That's the wavelength. Now today we proceed on to learn about another two terms called the frequency and period. Frequency and period. Okay, these two very important terms. Uh, After which you will learn about wave speed and the wave equation, the three wave equation. Okay, so first of all, let's talk about frequency. The relationship between frequency and the and the wavelength. Okay, if I can show you a very simple demo here, take a look at this demo. If I make this, um, take a ruler to measure wavelength, take a look at how the wave is created. Transverse wave, the wave motion is moving, this way and is perpendicular to the direction of vibration. Okay, so there you have a transverse wave. If I pause right now, this is a certain frequency. Later I'm going to increase the frequency. Okay, if I pause right now, you can measure the wavelength. Ready, pause. Okay, you can measure the wavelength, one complete wave. All right, one complete wave. All right, uh, it's about one complete wave is about 4 cm. About, okay, one complete letter F, estimate about 4 cm. But now I increase the frequency. See, I increase the frequency. Let's see what happened to this source of vibration. What happened now? I still maintain the same amplitude still the same, but my frequency has increased. Okay, frequency increase, and I pause the wave now. Pause. Okay, one complete wave now. What happens to the wavelength? Notice what happened to the wavelength. The wavelength has decreased. I can see more wave. They are more crowded now. More crowded wave, but the wavelength has decreased. Okay, one complete letter wave now is about 2.5 cm. Just now was about 4 cm. Now is about 2.5 cm. So I noticed something. As my frequency increase, because I increase the source, I increase the source of vibration, the vibration of the source. By making this vibrating faster, I make more wave per second. I see a decrease in the wavelength. As my frequency increase, my wavelength decrease. There is a inverse relationship. We notice from there. So from this simple demo here, we first define what is wavelength. We first define wavelength is the number. It is the number of complete wave produced or generated per second. That means in 1 second, how many wave is produced. That's how many hertz in frequency. Hertz. Okay, how many hertz in frequency here. Okay, which means if 1 second I see 20 waves, 20 complete letter S, 20 wave. That means the frequency is 20 hertz. That's what it means. How many wave completed in 1 second per second? That's frequency. Something similar to what you learn in pendulum. Number of complete oscillation or complete swing produced per second. This word per second, very important. Okay, so it is dependent. Notice it is dependent on the source that creates the wave. If I want to increase the frequency, I must make the source, the one vibrating the wave, causing the wave to vibrate faster. So you take a look at these two simple diagrams here, diagram A, diagram B. Diagram B has a higher frequency. You can see more wave, okay, more crowded, more wave produced per second. And by looking at their wavelength, you notice that the wavelength has decreased. With higher frequency, the wavelength decreases. There is an inverse relationship, which you can tell from the wave equation later on, the third formula. But before that, I need to bring to you the second terms, the second term called the period. This is a little bit confusing, but so long you memorize the definition well, you will not be confused. Period is talking about the time produced, the time taken, the time to generate, or the time taken to produce one complete wave. Okay, one complete wave take how much time? That's the period. Different from frequency. Frequency is the number of complete wave. This is the time taken. Okay, time taken. And their formula is related to one another in this form. T equal 1 over F, or F equal 1 over T. Period is T, measured in second. Okay, this one is measured in second. Measured in second. All right. When you take 1 over second, you get hertz. All right. When you take 1 divided by period in second, you will get frequency in hertz. Okay, frequency in hertz. All right. Okay, take a quick look at the relationship on the right hand side. Very quickly, we are going to study about period and frequency. Periods and frequency. I highlight again. Period is about what? Period is about time taken to produce one wave, to produce or create one wave. Okay, time taken to produce one wave. Frequency is number of complete wave produced in what? In 1 second. Okay, now I draw from this very simple diagram. Do you notice? I see a 1 second here. This time the x-axis is a time. Previous lesson, the x-axis is distance for you to measure wavelength. You can measure wavelength on the x-axis. Okay? But this time, to tell periods and frequency, you need the x-axis to be the time, to be in time per second. It could be minutes. Okay? So have to check this very carefully. So how do I tell the frequency very quickly from this wave? Because I do see a duration of 1 second. 1 second. Notice? 1 second. In this 1 second, how many waves do I see created? Let's take a look. I see one complete letter S. See, one complete letter S means one wave. One wave produced in 1 second, therefore, my frequency is 1 hertz. It's as simple as that. The frequency is 1 hertz. Alright? 1 hertz. Let's also look at the period time for this wave. Period time. Period time. Period is the time taken for one wave. What is the time taken to produce one wave? The time taken is 1 second. So the period is 1 second also. Period is 1 second. Time taken to produce one wave. 1 second. Frequency is 1 second. I see only one wave, so 1 hertz. Let's take a look at the second diagram to understand a little bit better. Okay, understand. This time, can you tell me what is the frequency? Number of wave produced per second? Per second. Let's see. This time, it is 1 wave, 1 letter S. 2 wave, 2 letter S. 2 wave. Time taken, 1 second. Within 1 second, I see 2 complete wave. So the frequency is 2 hertz. It's as simple as that. Okay, 2 hertz. But let's look at the period time. Period time is time taken for one complete wave. Time taken for one complete wave, 1 letter S like that. The time taken is here. That's the period T. And this time is within the 1 second, you see two waves. So one wave you got to divide by 2 is 0.5 or half second, 0.5 second, which means this time the period t is 0.5 second, time taken to produce one wave. Do you see a relationship very quickly from here? T is equals to 1 over f. If I know the f is 2, it is 1 over 2 hertz, which I get 0.5 second. There, okay? That's how the relationship comes about. When frequency increase, period decrease. Okay? Frequency and period, their relationship is inversely related. This one you try yourself. Take a look. This time the 1 second is here very clearly. 1 second is here. How many waves do you see? Take a quick count. Okay, do you see 4 waves? If you see 4 waves, then the frequency is 4 hertz. Then what is the period? Time taken for one wave. Time taken for one wave. One wave. Time taken for one wave, which is here, t. Okay, so now you have to divide by 4, or t equals to 1 over f. Divide by 4, you get 0.25 seconds. So the relationship between frequency and period, you have to know it very well before we can talk about the full wave equation. Okay, later we have a couple of examples to practice, then you will know what I mean. Okay, what I mean. Now I would like to introduce the another two formula. First formula is frequency equal 1 over t, or t equal 1 over f. Second formula is about wave speed, because wave move, anything that move has speed, right? So wave speed is the speed of wave. Let's look at the definition. The speed of wave, or we can say distance travel by the wave in 1 second. In 1 second, distance travel by the wave in 1 second. You learn in primary school, speed equals to distance over time. In this chapter, distance is the wavelength. Distance is the wavelength measured, traveled by the wave. So it's wavelength. Okay, this one, wavelength. Time taken for one wave is the period. So it's wavelength over t. So distance over time, it can be wavelength over period. If you take out the 1 over t, all right, the formula becomes like that. Okay, the formulas become 1 over t times wavelength. Remember, 1 over t is also f, so the formula becomes v equal f times wavelength. Recall, wavelength symbol is lambda. Lambda is wavelength. Okay, lambda, this rule symbol is wavelength. So frequency times wavelength is your next formula. Now it's also good to know this one as a third formula lah. Just to let you know, it's good also to remember this as the third formula. Speed equals to distance over time is also one of a good formula to know. So actually, I encourage students to learn these three by heart. Number 1, t equal 1 over f, or f equal 1 over t. Number 2, speed equal distance over time. And number 3, v equal f lambda. These three formula know by heart for this chapter, then you can practice a few questions. It will be quite simple to solve them. Okay, we'll practice more when I see you again. Right. Maybe at this time I skip this example first. Let me go to solve a few questions with you to know what we mean by knowing these three formula. Will help a lot. Okay, these three formula. Turn with me to the next page. You see how progressively we practice from the simple use of this formula. Yeah. Okay, so let's take a look. The formula has got to do with a few symbol. More practices with wave, lambda, wavelength, frequency f, period t, time taken for one wave, and wave speed v. Okay, all has got to do with this. So now let's take a look at this example of the wave graph that is given, this transverse wave, and let's see what is given. Y-axis is given distance, x-axis is in time. Be very careful, it's in time. That tells me that I can read the frequency and the period from this. Now the question say, first part, calculate the period t. Calculate the period t. Okay, let's recall period t. Formula definition. Period is the time taken for one wave. Now this time you don't see 1 second, you see 0, 0 0.2, 0 0.4, 0 0.6. Many a times your wave graph comes with this kind of timing. You don't see a 1 second inside. You see 0 0.1, 0 0.2, 0 0.3. But it doesn't matter. So long you can see period, the problem is solved. So let's look at the period. Time taken for one wave. Time taken for one wave. One complete letter S. Do you see? The time period T is 0.4 second. So my T equals to 0.4 second. Okay, or 0.40. 0.40. Calculate the frequency. You need to calculate the frequency. So use the formula F equal 1 over T. You get 1 over 0.4. You have 2.5 hertz. Okay, 2.5 hertz. Now calculate the wavelength. Calculate the wave speed. If the wavelength lambda is given 4 cm, how do you calculate the wave speed? Okay, wave speed equals to V equal F lambda. Use this formula. You have your frequency already 2.5 hertz. You have your wavelength 4 cm, so you can straight away apply this formula. V equal F lambda. Okay, and you get your 2.5 hertz times 4 cm. So therefore your wave speed is 10 cm per second. 10 cm per second. Remember your wavelength is measured in cm, so your wave speed will be cm per second. Okay, take note of that. Now you try this yourself. I reduce the 3 parts question into 2 parts. You see whether you can get this yourself. Okay, I want you to straight away calculate frequency, which you cannot tell from the graph. In order to calculate the frequency, you need to know the period. So go ahead, find your period. Okay, what is the period? Time taken for one wave. Let's look at the one wave in this question. One complete wave, one letter S. You got 0.2 second. So frequency equal F equal 1 over T. You get 5 hertz this time. Okay, 5 complete wave produced per second. This time wave speed given is 8 cm per second. Can you help find the wavelength? Help find the wavelength. Okay, find the wavelength. So you can use the wave speed formula. V equal F lambda. V equal F lambda. Find the wavelength. Lambda equal V over F. You have your wave speed given. You have your frequency found in part 1. So your problem is solved. Okay, the answer must be in cm. You know why, right? 1.6 cm, because your speed is given in cm per second. Alright, related. The last one, you really try it yourself. This time from 3 parts to 2 parts. Now this time the question is reduced to only 1 part. But you need all these steps, like the one above, to recall how to do. Okay, now take some time to do this yourself. Given this graph, transverse wave, if the wavelength is 45 mm, calculate the wave speed. If the wavelength lambda is 45 mm, calculate the wave speed v. Wave speed v. Okay, you know v needs to be equals to f lambda. So you need to find your f first. You can pause here and check my answer. Okay, so f equal 1 over t. You can see from the graph the t is 0.04. That's where you get 25 hertz. From 25 hertz, then you use v equal f lambda, you would have been able to find 1130 mm per second. Mm per second. Why? Because your wavelength is measured in mm. Must I change it to meter or not? You don't need to change unless the question says so. All right, unless the question says so. You decide the units you want, because in O level, remember, the when you enter the answer, it doesn't come with unit. You decide the units you want, unless the question say give your answer in SI unit for the speed. Then you need to convert the mm to meter, divide by 1000. Okay, becomes 0.045 meter, right? Okay, so I at this time I also want to ask you, what does it mean by 25 hertz? You may want to put this question in your notes. What does it mean by what does it mean by 25 hertz? What does 25 hertz means to you in English sentence? Tell me what it means. A lot of students say it means the frequency is 25 hertz. That doesn't answer it. You need to tell me what it means in terms of wave. Okay, in terms of wave. So recall, what is frequency? Frequency is number of wave produced per second. So what does 25 hertz means? It means 25 wave produced per second. That's what you need to know how to answer as well. I put a star here. Okay, because it came out in O level before. What is meant by 25 megahertz? Megahertz, mega means million. So it means 25 million wave produced per second. All right, 25 million. You look at today's the speed of the computer. Okay, computer speed. We talk about megahertz. Okay, the frequency is in megahertz. All right, and even gigahertz is times 10 to the power of 9. All right. Okay, at your own time also take a look at how to try this question at the back here. Question at the back here. All right. I give you two wave. Sometimes if your one structured question come in two wave, these two wave means they give you information that can help you calculate the wave speed. Let's look at the first wave. It gives you in x-axis in distance. So can you see it allows you to find your amplitude and wavelength. Amplitude, very easy, 0.7 is in cm, right? Amplitude, recall, amplitude, and it's in cm. So 0.7. Okay. How about wavelength? One complete letter S. One complete letter S. Okay. Wavelength. So is 20 measured in cm. 20 cm. Right? How about this one? Let's look at this one. Are you able to measure wavelength? Look at the time x. Look at the x-axis. This time is measured in time. Can you measure the wavelength? Answer is no. This one won't allow you to measure wavelength. But amplitude, you still can. Is 0.006 cm. Now, based on these two information, can you help calculate the wavelength if the speed given is 2 cm per second? Can you calculate the wavelength based on the information you gather from the diagram above? See whether you can get this answer 0.040 cm. Calculate the wavelength. Okay, if the speed given is this. There are two ways. I want to show you both formulas also work. First one, if you want to go for V equal F lambda, then you have to know your F first. You have to know your F. So calculate your F equal 1 over T. 1 over T, the T have to be gotten from the second graph, right? This graph, time taken for one wave. Time taken for one wave, 0.02. You look for the time axis to find your T. Okay, you have 50 hertz. Now from your 50 hertz, you apply V equal F lambda, you find your wavelength, 0.040 cm. I want to introduce the second formula which you learned just now. Is also very useful, using the speed equal distance over time, which you learned from primary school. Speed equal wavelength over period. You could have also solved it in one step. V equal wavelength over time. Wavelength is what you want to find. Wavelength is what you want to find, right? And the periodic time, period is 0.02, and is given the wave speed is 2 cm per second, and there you go. There you go, you have your wavelength times 2 times 0.02, you get 0.04 cm as well. Both method works. Okay, just to let you know, both formulas work, and it's good to know both of them. All right. Okay. At your own time, you should go and try to solve more questions from the worksheet given here behind. Try to do questions like this: question 7, 8, and 9. Okay, question 7, 8, and 9, as well as 4 and 5. 6, 7, 8, 9, 4, 5. I can review the answer to you later on. Okay, but go and try it at your own time. You can pause here, try, then check the answer. Check the answer later on. Okay, now don't always expect the question to be come with a graph. Okay, okay. The question can comes in the form of a problem sum like question 7. Question 7 is one example where they tell you frequency, they tell you wavelength, find the speed. Very straightforward. Okay, so you can pause here, try this few questions, then check my answer. I'll review the answer to you. Now you can pause here. Okay, now I show all the answer to you. You can do all the MCQ up to question 9 first. Okay, question 9. Let me make it smaller. Then you can see all the answer. Okay. Okay, so here's the answer. Take a look. All right, for this page. Hope you have done it yourself and checked through. Don't know, you can ask me. Okay, let's go up to one last part here called wavefront. Before that, maybe also try this question. Yeah, try this question. Vibration, just part A only. Part A. Part A. A vibration produce one complete wave in 0.2 seconds. What does that statement means to you? Instead of telling you the period is 0.2 seconds, they say one complete wave in 0.2 seconds. That means the period is 0.2 seconds. Okay, what is the frequency? Sometimes the frequency question asks like that. So F equal 1 over T, you would have found the answer. Then you carry on. If the wavelength is 0.8, wavelength means lambda. What is the wave speed? So you can apply this formula and find your answer too. Okay, find your answer. All right, so it's as straightforward as that. Now remember, just now I skipped something about how the particle move. This kind of question is very, very popular, also very popular in MCQ and structured question. So I'm going to give you a quick demo. Before that, you answer for yourself what is amplitude, what is the amplitude and wavelength here. What is the amplitude and wavelength? You can pause here, answer, then check. Okay, so right now I review the answer. You pause 2 first. Okay, now I review the answer to you. Okay, hope you got it right. Now, it's this type of question that I need to show a quick demo, part B. Okay, part B, you put a star there. The wave in the figure above is moving to the right. Can you see I put the direction, wave motion is to the right. And that's very important. This statement is very, very important. That will help us answer the particle P is moving what direction. Remember, for transverse wave, every particles only move up and down, up and down. But to answer this question, you have to tell very specifically, will it be moving up or moving down in the next second? If the wave were to be moving to the right, towards the right side, the wave motion is to the right side. In the next second, will point P be moving up or down? There is a way to find out this answer, okay, by superimposing the next wave. So I'm going to give you a quick demo now. Quick demo, see. So if I'm able to move like that, take a look. I copy this wave, and since they say wave direction is towards the right, I shift this wave a little bit to the right. A little bit to the right. So this wave is going to move towards the right. I superimpose this same wave, but just a little bit to the right. Now you can see that this particle, in order to move to the next position, which is to the new position, he has to come downward to this new red color position. He has to move downward. You will notice this answer will be different if the wave were to move towards the left. See, let me repeat. I erased my answer. Let me repeat. Let's shift this one to the back to the original position. Let's say my wave is moving the other direction. Let's say wave motion is this direction. Okay, the motion. Let's say the motion in the question say the wave move towards the left. Then you will have to move the wave. The next second he will move slightly to the left. Okay, slightly to the left. Now for the particle P to move to the new red color position, he has to move upward. The answer change. Okay, so that is the trick. But you see, it's only the wave involved is only in particular to where P is. You actually don't have to superimpose the entire wave. Let me take away this entire wave. Okay, let's see. Let me take this entire wave away. You could have just used the one wave at where P is. You just draw this simple wave, this position. Okay, let's go back to the original question. Okay, I actually just need to copy this part of the wave, where P is, and shift a little bit to the right because the wave direction is to the right. So shift a little bit. Then you can tell the answer already. From here, you can already tell the answer that P got to move downward to this blue position. Okay, move downward. So back to the question. Any problem, come back to me again. Back to this position. So just now from the demo, the answer is he will move downward, right? Then he will move downward. Okay, give yourself a practice. There was one question here. There's one question. The answer also depends on where the particle P is. Okay, so let's take a look at this question. Question 12. Take a look. They give you two particles, P and Q, and they tell you something very important. Wave direction is towards the right. Exercise the same method just now. Then you give me the answer. You can pause here. Okay, superimpose your wave slightly to the right the next second and see how will P and Q move. Then answer the question. What will happen next? Okay, will P move to the right? That's ridiculous, right? They only move up and down, right? Will P move up? That is possible. Will Q not be moving? I'm not sure. Okay, will Q be moving up? So you check what with the new position, how will P and Q move? You pause here, get your answer. Now check my answer. My answer is D. I hope you got that right. You got it right means you know how to answer this kind of question already. Okay, now come to the last part called the wavefront. What does wavefront means? Okay, what does wavefront means? Wavefront, let me pause here first. I need to look for one YouTube, one video clip that define wavefronts very well. Okay, I want to start introducing this wavefront by looking at this video clip. Take a look at this video clip. Wavefront means taking all the particle on the surface that's moving in the same direction and in the same speed, same motion. Join them with one imaginary line. There you go. You will see a wavefront. Take a look at this video clip very quickly. Let me play. Where's the play? Okay, see. So this is one wavelength, right? So if this is one wave, if I introduce more wave, and take all the points on the crest, and join them with a line. And imagine you are seeing this water wave from the top. You are seeing this water wave from the top, not from the side. From the side, you see like that, right? Transverse wave. But if you see from the top, that means you look from the top down onto the pond. What you see is black lines, one black line after another. You throw a stone into the pond and you see the black and white lines coming out, forming the wave, the water ripple coming out in lines. These lines that you see on the top of the water surface, this imaginary line that join all the crests together, that means all these points, all these particles on the crest, they are moving together in the same direction, in the same speed. They are all going to go down in the next motion. Okay, so they are called the particles moving in phase. When you take the line joining them, that line is called wavefront. And you notice that since wavelength is measured from one crest to the next crest, the distance between two lines, two immediate lines, two consecutive lines is also known as one wavelength. So wavefronts are just lines of wave that you see from the top view instead of side view. Okay, you have to know this term very well, because many a times your diagram comes in the form of wavefront also. There are straight wavefronts, straight lines wavefront, which we call the plane wave. There are also circular wavefront, like you throw a stone onto the pond. What you get is a circular wavefront. Okay, so this one is example of wavefront, and we go back to your notes now. If you go back to your notes, you need to learn this definition by heart. I put this 3 star here. Okay, so it's an imaginary line on the wave that joins all points which have the same phase. The word phase means same speed, same direction. Okay, same phase of vibration. Same phase of vibration. Learn this word for word. Very important. Only these two lines. The one at the bottom is not so important. Okay, the definition of wavefront. The direction of wavefront, so only this front part you need to memorize by heart. Okay, the one below is just for awareness. This one is just for awareness. The direction of wave motion is always perpendicular to the wavefront. That means when the wave, you drop a rock or a stone onto the pond, the circular wave move outward like that. Move outward this way. The direction of wave motion, the way the water ripple move out, is perpendicular to each wavefront. Is perpendicular. You can see I draw 90 degree to each of them. The wave motion is always perpendicular to the motion of the ripple, which is the definition of transverse wave. All right, it's a transverse wave. Okay, we are still talking about transverse wave. Now, I'm going to introduce you how we show ripple in the science lab using this thing called ripple tank. Okay, this thing called ripple tank. Okay, how we show this kind of wave, the wavefront using ripple tank. Ripple tank. I show it in the video clip next. You take a look at the video clip. Ripple tank looks like this. Okay, looks like this. Very quickly. Okay, I pause here first. You can see this rod here. This rod here is vibrating up and down. Okay, with this motor. This motor causes it to vibrate. Okay, the frequency, what kind of wave produced, that means how close or how crowded the wave is, the frequency per second is determined by this source of vibration, this piece of wooden plank, how fast it vibrate. If it vibrate very fast, you get very high frequency. If it vibrate very slow, then you get very low frequency. That means the wave will be quite far apart. Okay, so let's take a look. And then using the light, cast a shadow onto the piece of paper at the bottom. You will see lines, and black lines and white lines. And that is called your wavefront from the ripple created up here. So this is a small little tray, water tray called a ripple tank. So we are creating water ripple using this plank of wood that vibrates up and down. Okay, so let's see. Let's continue. Take a look. So it's vibrating, and there you create a plane wave, straight wave. Okay, let me fast forward. You create the plane wave, and if you look down below, this is how the wave is projected. The wavefront, the shadow projected on this white paper screen, white paper, and with a ruler there you can measure the distance between two black lines. That is your wave length, your wavelength. All right. Okay, so this is an example of a wavefront. created using the ripple tank. Let me pause here and also show you how we create deep and shallow region, by introducing one piece of acrylic plate into the ripple tank. I will create a region of a shallow region as compared to a deep region. So it's for studying when the water wave is created and they move from deeper to shallow region, how will the wavelength, wave speed or frequency change? Will it change or not? Let's take a look at the next clip. Next clip. Next clip, I need to introduce this one. Uh, Take a quick look. Can you see one piece of trapezium? I'm drawing it. I'm showing you now. One piece of trapezium acrylic plate, hard plastic plate, introduced into this water pool, this ripple tank here. That means this region here now there is a step upward step, and that gives you the shallow region. This part is the shallow region, whereas the part outside here is the deeper region. Okay, deeper region. So now if it again, when the ripple is created, let's see whether there's a difference when the wave move out from the source of vibration coming towards from the deep region here, come to the shallow region here. This one, because you create a step upward, right? This, when it comes from deep to shallow region, whether there's a change in their wavelength, wave speed, and so on. So let's take a look now. Okay, at the shadow here, can you see? This part is the, I pause again. This part is the shallow region, the trapezium platform. This part is the deep region, original deep region. So the wavelength, the wave is good. The water ripple created the wave black lines. The wavefront is going to move from deep to shallow. Let's see how the wave change. Okay. See or not? I pause. I pause. Okay. Down here the wavelength. You can use white lines to see. It doesn't matter. White line also represent the wavelength. Okay. The wavelength is this part like that. Okay. One white line to the next. This is the deeper region wavelength. When it comes to the shallow region, do you notice it bend backward? Bend backward. This is the deep region. Shallow region, it bend backward. What does it imply to the wave speed at this shallow region? The fact that it lag behind. They get dragged behind. That means when they enter into the deeper region, they slow down. That's why they are slack behind. Behind, bend backward. Whereas this one in the deep region move forward in the front. This one is dragged behind at the backward. Okay, as the wave come out this way, right? And you can see because they bend backward, their distance, the distance between two white lines, the wavelength also become shorter. So wavelength becomes shorter, wave speed becomes slower, but frequency remains the same. Why? Because the frequency depends on the source that is vibrating and beating on the water surface. If that source keep going in the same speed of vibration, then the frequency, whether it's deep or shallow region, the number of wave produced per second will still be the same, because the source did not go any faster or slower. The speed has been the same. You want frequency to change, you need the source to change its speed. But throughout this wave movement from deep to shallow, the source of vibration is still going at the same speed, so his frequency did not change. Later we also take a look at the formula, the relationship between the three of them, the three variables in the wave speed equation. When two of them change, one must remain constant, which is the frequency. Okay, the frequency. So let me go back to this the notes, and we end at there. The notes here. Okay, so if I take a look at this side view, okay, side view, talking about the side view, if you take a look at this video clip as well, very quickly, this video clip from the applet, this one is also very good there. In the way it introduced like what ripple tank is. Take a look. I will start it. See if this is the wave created because of the consistent dropping of the water droplets from the tap. So it's very consistent, the timing. So this is the frequency you get, the wave. Okay, And if I go side view, now I go, this is side view, I go top view and see, look at the wavefront. This is what you will see. Take a look. This is what you see. Black and white lines. This is called wavefronts. Okay, let's go back to the side view and make it go. Can I go faster a little bit? Yeah, can I increase the frequency? Okay, increase the frequency. See, as I increase the frequency, the wave now gets more crowded. You see more waves, right? Wavelength decreases. Wavelength decreases. And if I see the top view for wavefront again, this is what you see now. Okay? The distance between each line become shorter. If I want to see plane wave, this is what I can show you. Plane wave. If I want to see plane wave, wait, can I show plane wave very quickly? Plane wave is this one. Okay. Let's move. Okay, plane wave now. Plane wave means straight wave, straight line, straight wave front. I need a rod to vibrate. The rod, vibrating rod. Okay? The whole rod beat on the water surface. But I can't show you side view. There's no side view to show you. This is how you create. If I increase the wavelength, I want to increase the frequency, means now this source has to vibrate faster. Okay? Vibrate faster. If I vibrate faster, then the line become closer. All right, you get the idea, right? Now, back to the notes. Now, back to the notes. Now, what you need to know is the changes that happens between deep region and the shallow region. Deep region, shallow region. The shallow is this part. Okay. Can you continue drawing the wave now? Deep region, they show wavelength here to here, longer wavelength here to here. Okay. Short, come to the shallow region, the wavelength decrease. Just now we saw the demo of the ripple tank. The wavelength decreases. Okay, they become shorter. And because they become shorter, and if I see from the top view, take a look at the top view. Now I see the wavefront. Every black line represent the crest. Okay, if I compare with the side view, every black line represent the crest, the topmost particle on the water wave. Then you can see that when they enter the shallow region, the wavelength becomes shorter. And these are the properties you need to know, the changes in the properties. As the wave travel from deep to shallow region, what happened to the wavelength? The wavelength decreases, becomes shorter. Okay? The frequency remains the same because it depends on the source. The source don't change, it will remain the same. And the wave speed will decrease, meaning it becomes slower at the shallow region. Notice how you can remember this very effectively. Shallow start with the letter S. Shallow start with the letter S. Wavelength becomes shorter, also start with S. Frequency remain the same, start with S. Wave speed becomes slower, start with S. Okay? For shallow region, wavelength, everything has got to do with S. Shorter, slower, same frequency. Okay? So that's what you have to know. Now this one is just for you to have an awareness of how the wavelength bend, how the wavefront bend when you go from deep to this shallow region. Just now we saw on the demo inside the ripple tank, the wavefront. When this line come this way, all these are full wavelength, right? This one give you a full wavelength, but this one is not complete, 3/4 complete only. The next 1/4 is in the shallow. It has to get dragged behind like that. Okay, the wave is coming this way, the wave is coming this way. Okay, coming this way. Now this one is 1/4 in the deep region. The next 3/4 will get dragged behind, slower, get dragged behind like that. The next full complete wave is inside already, is inside the shallow region, and it will follow this same wavelength. with this short. Follow this same wavelength to be uniform wavelength, this short as well. Now this one is complete wave, and consistent short wavelength now. So that's how the wave change direction. The direction is changed. All right. Okay. The direction is changed this way, and the wavelength, uh, meaning the wavelength also decrease. If you notice that, okay, it goes this direction now. Previously was this direction. Now the direction change. Slow down. Okay, with a shorter wavelength and slower speed, but frequency remains the same. Now, based on that, you can try answer these 3 questions below, and that's the end of this topic. That's the end of this topic. I had the class try these 2 questions, question 10 and question 11, about deep and shallow region. So the deep and shallow region is represented by this triangular part, the triangular platform introduced. Okay, sorry. The triangular platform introduced is the shallow region. Okay, this region is the shallow region. So when the wavefront, water ripple go out this direction, how should the wave front change when it enter the triangular shallow region? Okay, try this yourself. Eliminate all the impossible answer. Okay, first, then make your best study on the correct one. Then question 11 also, you have a wave going from shallow, not shallow, going from this speed V1 to this speed V2, these 2 region P and Q. You are going to deduce based on the wavelength that you see there, to deduce which side is deeper, which side is shallower, and then study the answer. Okay, and you can pause here, get your best answer, then check with mine. Okay, so first answer is C. Second answer is D. All right. Why? Let's look at question 10. Let's eliminate the impossible answer. I will eliminate A and B. A and B. Why? Because it shows the wave outside this deeper region and the inside shallow region, one straight line through as if the direction did not change. That is impossible. Okay, it cannot be going straight. And this one, same, the deeper region and the shallow region, one straight line in without changing, without bending. The line didn't bend. So these are impossible answer. You are left with either C or D, right? Why I choose C? Because it shows that at the deeper region, while the wave are still at the deeper region here outside, while the wave is going this way, can you see in the shallow region, they get dragged behind. They get dragged slower behind, dragged as compared to those outside, as the wave go this direction, outward. Okay, the one in the center get dragged behind. Okay, get dragged behind. I hope you see that. So that tells me in the shallow region, they are traveling slower. Therefore, the answer is C. I can also see that because they are dragged behind, their wave length is shorter as compared to those outside wavelength. Now take a look at D. Although it bend also, but they are bending forward as compared to their line outside. Bending forward means they are moving faster ahead than those that are outside. They should not be moving faster in the shallow region. They should be moving at the slower region. Also, by bending forward, you can tell the wave speed is longer as compared to the wavelength is longer at the inside as compared to the wavelength that is shorter on the outside, which is wrong. Okay, because in the shallow region, it should be shorter. All right, I hope that explains it. Now, question 11, by looking at the wavelength, you can deduce that region P is the deeper or shallow. It is the shorter wavelength, right? So it's shallow region. This one is the deeper region. Okay, in deeper region, let's look at the speed. The speed. wave speed in the deeper region should be faster. Shallow region should be slower. Slower. Let's write it down. Slower. It should be slower. Okay? Which means V2 should be greater than V1. Because V2 should be the faster one. Deeper region faster. V1 slower. Okay? That should tell you already. Then wavelength. Wavelength, if this is lambda 1, this is lambda 2, this side is lambda 2, that tells me lambda 2 must be greater than lambda 1 wavelength. Okay? Shorter. In shallower region, it should be shorter. Alright? And that ends our chapter for this. That ends our lesson for this chapter. Okay? More questions will be given to you for wave equation. Because some students are requesting for that. I will give you that worksheet to practice in our holiday uh, program on Monday. Meanwhile, you do this few as homework and check the answer also. Question 15. All right. Check the answer. You can pause here and then check my answer. Okay. I review the answer here. Okay. This answer was erased away, but you will know you can go and calculate and find the answer in hertz. Okay, I will stop here. Thank you. Similarly, this question as well. You can pause here and find out this answer. Okay, see you in the holiday.